Hi everyone. In this video, we will look at a number of examples of different sequences of functions with particular emphasis on in what ways those sequences of functions converge. We saw in the previous video that in addition to the pointwise and uniform convergence that we saw in Math 5610, there are other modes of convergence, such as pointwise almost everywhere, uniform almost everywhere, almost uniform in measure and in mean. We want to continue working with those in this video by seeing how they apply to these different examples. I want to begin by revisiting this example we were looking at the end of the last video. So this was the sequence of functions defined on the closed interval 0, 1 by f sub n of x is equal to n times the characteristic function of the interval 0 to 1 over n. So you will recall last time that this sequence of functions began with the constant function 1. Then the height doubled on the interval 0 to 1/2, but then was 0 elsewhere. Then tripled on the interval 0 to 1/3, but was 0 elsewhere, so on and so on. So we observed last time, as it relates to these different modes of convergence, that this sequence of functions does indeed converge piecewise almost everywhere. So we're going to have today sort of these different boxes, and so we can check that this sequence of functions does indeed converge. Sorry, I think I said piecewise, pointwise almost everywhere. We saw last time that this does converge almost uniformly. So why does this converge almost uniformly? Well, if I look on the interval E, but I delete the interval, say, 0 to epsilon, for any epsilon, then there exists some capital N, some natural number capital N, such that f sub n of x is actually just equal to 0 on E delete 0 epsilon for all little n greater than capital N. So what happens here is you pick whatever epsilon you want, right? Or sorry, you don't pick the epsilon. The epsilon is given. So you remove this interval 0 epsilon, right? Well, eventually, this is only non-zero on the set 0 to 1 over n. So eventually, what happens is that 1 over n moves inside of this range from 0 to epsilon, right? Well, once that happens, then your function is 0 everywhere outside of here, okay? And so since f sub n is 0 for all n beyond capital N, this means that f sub n converges to 0 uniformly on E delete this set 0 epsilon, okay? So I can do this for every epsilon. I can find this set so that f sub n converges uniformly on E delete that set, and that set has measure not more than epsilon, okay? So in addition to converging piecewise, this also converges almost uniformly. Oops, I think I missed the checkbox there. Okay. Now, this does fail to converge uniformly almost everywhere. Now, why is that? Well, I mean, really the issue is I have a problem with the convergence at 0. And to fix it, to get uniform convergence, I need to remove some neighborhood around 0. But any neighborhood around 0 has strictly positive measure. So I cannot say that it converges uniformly almost everywhere because I have to delete an entire interval to get uniform convergence. Okay. And then finally, if we look at this and think about it in terms of in measure and in mean. So recall that to converge in measure, I want to look at the limit as n goes to infinity of the measure of the set of all x values in my domain, such that f sub n of x and f of x differ by more than epsilon. And what we said last time is, well, this set, right, for this particular sequence of functions, this set is always a subset of 0 to 1 over n. Because if I think about this sequence of functions, the only place they differ at all from 0 is on this interval 0 to 1 over n. Okay. Therefore, the measure of this set must be less than or equal to the measure of this set by monotonicity of the measure. So this is less than or equal to the limit as n goes to infinity of the measure of 0 to 1 over n. Okay. But of course, that's just this is an interval, so its measure is just the length, and that goes to 0. And since the limit as n goes to infinity of the measure of this set is 0, that's exactly what we mean by converges in measure. So this sequence of functions does indeed converge in measure. Okay. The final one we have is in mean. Okay, so recall that to converge in mean, we need to look at a slightly different limit. To converge in mean, we need to look at the limit as n goes to infinity of the integral of f sub n minus f in absolute values d mu. Well, in this case, the pointwise limit here is simply 0. So minus 0, we really just need to look at this. Okay. These are all non-negative, so in fact, we can also remove the absolute values. Okay. And so now we ask ourselves, well, what is the integral of this function? Well, this function is actually Riemann integrable, so its Lebesgue integral is equal to the Riemann integral. It's really just a rectangle with height n and base 1 over n. So each of the integrals is actually 1. Right? Each of these integrals, regardless of which n you're at, has value 1. So this limit is 1, which is not 0. And 0 is what we need in order to have convergence in mean. So this fails to converge in mean. I missed the box again there. All right. Now, this is sort of just a recap. We've seen this sequence of functions before. And what we want to do today is we want to sort of go through several different examples and just sort of go through this checklist. Can we determine whether they converge pointwise almost everywhere, almost uniformly, uniformly almost everywhere, in measure and in mean? Right? Now you notice I've taken off pointwise and uniform, mostly because we've done those plenty in 5610, and I'll point out in some places where things actually converge maybe just pointwise or just uniformly. But we want to walk through this, and what we'll do at the end, we'll have built all of these sort of rows of a table up. So we'll have it for all these different examples. And notice that, so what can I tell from something like this? So from this example, right, this shows me that convergence in measure cannot imply convergence in mean. Why? Because now I have an example of a function which converges in measure but not in mean, right? Pointwise almost everywhere convergence cannot imply convergence in mean. Why? Because here's an example where I have pointwise almost everywhere convergence but not convergence in mean. So again, we see sort of through some of these examples, it starts to give us an idea of what types of convergence might imply other types, or actually in this case, what types do not imply other types. So again, our focus today is going to be on just strengthening our understanding of what these different modes of convergence are, while also beginning to think about the relationships that may exist between these different types of convergence. All right, so let's look at another example. So this is nearly identical. This is what I'm going to call the fast decay spike. It is the function which is n times the characteristic function of the interval 0 to 1 over n squared. Okay. Now, we're going to step through this fairly quickly because most of the arguments are exactly the same. So it converges pointwise almost everywhere to 0, right? The only place you sort of have an issue is at 0, right? In fact, in some ways, it's converging faster because this interval is shrinking faster. So great, I get pointwise almost everywhere convergence. I get almost uniform convergence. That same sort of argument from before of take any interval 0 to epsilon, right? If you remove it, you get uniform convergence on that interval. So almost uniform convergence, check. You still do not get uniform almost everywhere convergence, right? Again, same problem. You need to really remove a neighborhood around 0, but that set has positive measure. So we don't get uniform almost everywhere convergence. Okay. We get convergence in measure. Again, same idea from before, right? You look at that limit. Now that set where it's non-zero is 1 over n squared, its limit still goes to 0. So great. Now, the one thing that really changes here is the n mean piece. So let's look at that. Now I want to look at the limit as n goes to infinity of the integral of f sub n minus f d mu. Okay. Same thing as before. Okay. This f is just 0. This I can drop the absolute values because it's a non-negative function. But now the difference is these are rectangles with height n and base 1 over n squared. So each of these integrals, for a fixed n, it comes out to be n times 1 over n squared, or 1 over n is the area under the curve. But that goes to 0. All right. So this, in fact, gives me convergence in mean as well. So here, by just sort of changing this indicator function slightly, right, I can now get convergence in mean in addition to this convergence in measure. Okay. Now here I want to flip things around a little bit with this example. We've been looking at examples where things are sort of collapsing towards a single point. Now I want to look at things that are sort of running away. Okay, so here, instead of taking my domain to be the interval 0, 1, I'm going to take my domain to be all of R, right? Or you could take this to just be the positive reals, but we'll just take it to be all of R. Okay. And I'm going to define f sub n of x to be the characteristic function of the closed interval n to n plus 1. So, sort of think about what's happening here. So you have height 1, okay, and you have 1, 2, 3, 4, 5, 6, so on and so on. All right. So when n is equal to 1, what do I get? I get the characteristic function of the interval from 1 to 2. So the first function just looks like this and is 0 everywhere else. Okay. The second function, right? So n is 2. This is just a characteristic function of the interval from 2 to 3. So this is just so you can see this is called the escaping bump because what's happening is as your sequence moves out, this bump is just moving to the right 1 every time. Okay. Now, let's think about what are the implications for that. And this is one that I think It feels a little counterintuitive to some people, and it certainly felt counterintuitive to me the first time I saw it. And in part, this bit that's counterintuitive is actually real, is sort of revealing something deeper that's going on, which is that we're now working on a set that has infinite measure instead of finite measure. And because it has infinite measure, there are ways, there's sort of stranger ways things can run off. Okay. So in particular, I think the first time I saw this, I even felt uncomfortable with the notion that this converged pointwise. Okay. But it does converge pointwise. Let's sort of think about why that's true. Okay. So fix a point X in your domain. And let's call it X star. Well, eventually, no matter how big your X star is, right? Eventually, the bump moves past X star, right? And once the bump has moved past X star, then F sub n of X star will just be equal to 0. So for all n beyond some cutoff, right? So you can pick a natural number that's greater than X star, okay? Then F sub n of X will be equal to 0 for all little n greater than that natural number, right? And so F sub n of X star converges to 0, okay? So we do get pointwise almost everywhere convergence. In fact, we actually just get pointwise convergence. Okay? It's not even, you don't even need the almost everywhere piece, right? It's just straight up pointwise convergence, okay? All right. Now let's think about whether or not this convergence is almost uniform. Okay. Now, what would I need for almost uniform? For almost uniform, I say for every epsilon, I should be able to remove some set of measure less than epsilon and have this sequence converge uniformly on that set. Okay. So the problem here is, right, I need to be able to pick one n that works for everything. Now, pointwise, this converges to 0, okay? So F sub n converges to 0 pointwise. Okay, so if it converges uniformly, 0 has to be the limit. But note that there's always some x value, which is distance 1 away from the pointwise limit, okay? So certainly this does not converge uniformly, okay? So another way to say this is, right, you know that the supremum over all reals of f sub n of x minus f of x, it's always 1, right? Irrespective of what n you're at, there's always some point where the f sub n is distance 1 away from this, okay? So in particular, you certainly can't get these two within epsilon of each other for any real, for every real value. Okay. Now, that's not almost uniform though. So almost uniform says, well, what if I'm allowed to remove a set of measure epsilon? Well, if epsilon is bigger than 1, great, right? If epsilon was bigger than 1, you might think, oh, I'll just remove this whole interval. But remember that this bump is moving, and so even doing that won't work, right? But you can also imagine that when epsilon gets small, right? If you can only remove this little set, and then you want to try and show that it converges uniformly on everything else, well, this bump is still moving. So eventually it's going to move out of this set as well. Okay. So you're actually not even going to get almost uniform convergence here. Okay. So you get piecewise, but not almost uniform. You do not get uniform almost everywhere, right? So these sorts of uniform convergence are out. Okay. Now you might wonder about in measure or in mean. So in measure, we need to think about, right, the measure of this set, the set of all x, such that f sub n of x minus f of x is greater than epsilon. Right. Well, I need to show that the limit, if this is going to converge in measure, I need to show this limit is 0, and I need to show that for every epsilon. Well, let's say I take epsilon is equal to 1/2. And let's just look at that case. If I take epsilon is equal to 1/2, then this set is really just asking, for what values is f sub n of x minus f of x, for what values are they different? Because this only takes the values 0 and 1. This is 0. Okay. So the set of all x values where the difference between f sub n of x and the 0 function is greater than 1/2 is exactly the set n to n plus 1. Okay. So this is just the limit as n goes to infinity of the measure of the interval n to n plus 1. But the measure of an interval is just its length. So this is the limit as n goes to infinity of length of that interval is 1. So this is 1. So there is an epsilon for which this limit is not 0. Therefore, it does not converge in measure, because to converge in measure, for every epsilon I put here, this limit would have to be 0. So it does not converge in measure. If we want to think about in mean, then we just need to look at a slightly different limit, right? We need to look at this limit involving integrals. And here I'm integrating, right, just to emphasize, I'm integrating over all of R. Okay. This integral, right, this is f is 0. This is just that bump that has base 1 and height 1. So this integral is just 1 for every n. So this is 1, which is not 0. And since it's not 0, I do not get convergence in mean. Right. So here I have an example of a function that converges pointwise but does not converge in any other way. Okay, so what does this sort of show me? In one way, it shows me that pointwise convergence is like the weakest form of convergence, right? Because I can have things that converge pointwise almost everywhere, but don't converge in any other way. Okay, at least if I allow myself an infinite domain. Okay, whereas if I go back to say that the fast decay spike example, one thing that sort of shows me is that uniform almost everywhere convergence is a very strong form of convergence, because it's possible that a sequence of functions can converge in many ways but still fail to converge uniformly almost everywhere. So in some ways, what this is revealing is a sort of hierarchy of these forms of convergence where uniform things are at the top and pointwise things are at the bottom. Now, it's not a perfect stratification. Okay, so we'll see through more examples, but we're starting to reveal sort of some different characteristics, properties, relative strengths of these different types of convergence. Now, this next example is one that you've actually seen before, although I've expressed it slightly differently here. This is the so-called typewriter sequence, although again, it wasn't called that. So if you look on the interval 0, 1, so again, I'm back to just working on the interval 0, 1, then I'm going to enumerate what we call the dyadic intervals. And so the way I'm going to do that is I'm going to take the interval 0, 1 first. Then I'm going to cut that in half. And then I'm going to take the first half, 0 to 1/2, and then the second half, 1/2 to 1. Okay. Now I'm going to take and I'm going to cut everything in half again. So now I'm dealing with quarters. And so my fourth interval is going to be 0 to 1/4. My fifth interval will be 1/4 to 1/2. My sixth interval will be 1/2 to 3/4. And my seventh interval will be 3/4 to 1. Okay. And then I cut it in half again. So now I have eighths. So then I go 0 to 1/8, 1/8 to 1/4, 1/4 to 3/8, 3/8 to 1/2, right? And so I keep going in this way. Okay. And what I'm going to do is I'm going to define this sequence of functions to be the characteristic function of this sequence of intervals. Okay. So again, sort of graphically, right, I start with sort of 0, 1. Okay, there's my first function, right? Then I cut in half and I get this function first, And then this function second. Okay. And so it's called the typewriter function because things are, as something goes down, something else comes up, sort of like old typewriter keys, right? And so, and sorry, actually it's not about the keys. I mean, it does sort of work like the keys. So this thing moves, it gets all the way to the end, and then it comes back and it starts working its way back across the interval again. So it goes 0, 1/2, sort of 0, 1/2, then 1/2, 1. Then we bring everything back, and then we go across in steps of 1/4, right? And so it's like on old-timey typewriters, you had to push the return all the way back, right? So you got to the end, and then you push the thing all the way back. So it's sort of working the way across, and push, come all the way back. Okay. All right. Now, let's think about what this sequence of functions does. All right. So this sequence of functions, right, it does not converge pointwise. Okay. Let's think about why. So it's really that sort of typewriter feature we were just talking about. So take some x value in here. Okay. Well, to start with, in the first function, the f of x star will be 1. Okay. Now, then I'm going to split my interval in half. Now, of the two intervals that have length 1/2, at least one of them contains x star. So the function value will be 1 on at least one of those. Okay, let's say 0 on the other, unless x star happens to be 1/2. Okay. Then let's take and then we break it up into fourths. Well, again, this will be contained most likely in just one, but at most two of those intervals. So it's going to be 0 sometimes and then 1 at least one time. Okay. Then you break it into eighths. Well, then it's going to be 0. It's going to be 0 most of the time. It's going to be 1 either 1 or 2 times. Okay. So my point is that no matter how far you go out, there's always going to be times where this is 1 again, even though it's 0 most of the time. Okay. So you can go out a billion terms in the sequence. At some point, that sequence of functions is going to move its way across, and it's going to come back, and it's going to go again. Okay. So this fails to converge even pointwise almost everywhere. Now, you might say, well, Quinn, didn't you just say that, pointwise almost everywhere, that's the weakest form, so it must be everything else fails, right? Well, no, not quite. Okay. And that's where I was sort of giving myself some wiggle room there. This is not some strict hierarchy. And in fact, in many ways, it depends on your space here as well. So let's look through these others. Now, certainly, if it fails to converge pointwise almost everywhere, it's going to fail this uniform almost everywhere condition, right? Sorry, that's not. I'm sorry, that's not immediately true. That's the other way around. If it. Oh no, sorry. This is right. Since it fails to converge pointwise almost everywhere, it's not possible for it to converge uniformly almost everywhere. If it converged uniformly almost everywhere, it would be forced to converge pointwise almost everywhere. The one that we have to think about here is this almost uniform. And so I can ask myself, does this converge almost uniformly? And again, the answer here is going to be no. Again, the failure to converge, not only does it fail to converge pointwise almost everywhere, it fails to converge pointwise at even a single value. Okay, so this doesn't converge pointwise at all. It's certainly not going to converge almost uniformly. Now, the ones that are in question, though, really are these in measure and in mean. So let's think about these. So if I want to think about in measure, I want to look at the limit as n goes to infinity of the measure of all x and e, such that f sub n of x minus f of x is greater than epsilon. Now, here's where actually, we we don't even have necessarily a candidate for the limit function yet, right? Because it doesn't even converge pointwise. Often you use the pointwise limit, right? But this doesn't converge pointwise. So if I'm going to say it converges in measure, the first thing I have to ask is, well, to what, right? Well, it feels like zero might be a natural choice. I mean, it's never zero like forever at a particular point, but these intervals are getting small and it's zero in most of the other places. So let's guess zero. Okay. So, well, what is the limit as n goes to infinity of the measure of this set? Well, let's say I take epsilon. If I take epsilon to be 1, right, there are no points where f sub n of x and the zero function differ by more than 1. The most they ever differ is 1 because these are always characteristic functions. Okay, so if epsilon is greater than 0, if epsilon is greater than 1, then this is just the limit as n goes to infinity. There's nowhere where this differs by more than 1. So that's actually greater than or equal to 1. There's nowhere where this differs by more than 1. So if epsilon is greater than or equal to 1, then this is just the measure of the empty set, okay, which is, of course, 0. Okay, so we're good. We're good if epsilon is greater than 1. What if epsilon is less than 1, though? Well, if epsilon is less than 1, then certainly there are some places where the difference is bigger than epsilon. Okay, but let's think about what the lengths of each of those sets are. Okay, so when n is 1, well, that's everywhere. So it has length 1. So the sequence of values, so think about the limit as n goes to infinity. I'm just going to write out what this sequence of values is going to look like. So it's going to be 1. Then for the next two, they're intervals of length 1/2, where your function differs by more than epsilon. Then there's 4 of them with length 1/4. Okay. Then there's 8 of them with length 1/8. Okay, so on and so on. But as you go further and further out in this sequence is indeed converging to 0. It's converging slowly, but it is converging. Okay, so this limit is also equal to 0. So even though it fails to converge pointwise, it fails to converge almost uniformly, fails to converge uniformly almost everywhere, it does converge here in measure. Okay. Well, what about in mean? Okay. Well, what do I need to look at? If I want to look at convergence and mean, I've got to look at this other limit. So again, I need a candidate. I'm going to guess it's probably 0 again here. Okay, and here I'm just integrating over 0, 1. Okay, well, what are each of these integrals? Well, each of these integrals, right, they're the same as that sequence I wrote out earlier, right? Because the height of the function is just 1. So this is just the limit of this same sequence, 1/2, 1/2, 4, 1/4. Then we have 1/8, 8 times. Right? But this limit of this sequence is 0, right? So not only does this converge in measure, it also converges in mean. All right. So again, not only do we see that, this isn't some strict hierarchy. I think at this point you start to sense a little bit of a divide between these in measure, in mean things, right, and the pointwise uniform sort of continuum over here, right? Sort of feels like there's a little bit of a divide, although in certain cases some may imply others. Okay. So again, this typewriter sequence is a really nice example. It's sort of helpful anytime I want to come up with, I start thinking about something that doesn't converge pointwise. or whether I need that. Like this is a good example of something that does not, that fails to converge pointwise, and like fails really spectacularly. It does not converge pointwise for any x value, right, in the domain. It's not just that, oh, it converges pointwise except on some interval, right? No, this doesn't converge pointwise for any x value in the domain. Now, I want to take that example, the typewriter example, I want to modify it ever so slightly. So I want to take those same things, but I want to divide through here. We're going to call this the unit mass sliding bump. So what I'm going to do is I'm going to divide through by the measure of the interval. Okay. Now, maybe this seems a little complicated. This is actually, in a way, it's like we're combining the typewriter sequence with that the tall spike example. So what's happening here is, okay, in the first thing, you just get the indicator function of 0, 1. Okay. But now on the intervals that have lengths 1/2, you multiply by 2 out front. And on the intervals that have length 1/4, you multiply by a 4 out front. So what's happening here is that as these things move along, right, every time you go back, they double in height. Okay. Now, what does that change? Well, certainly that's not somehow going to miraculously cause things to converge pointwise. You should have, in fact, it's worse now. Not only are things jumping from 0 to 1, like not only are they jumping up to 1 every time you come back, but they're jumping to 1, then you come back, they jump to 2, next time they jump to 4, next time they jump to 8. Like these things are, it's even worse than before. Okay. So certainly they're not converging in any of these nicer ways. Okay. What about in measure or in mean? So in measure, now again, remember, convergence in measure, and this is really why I have this example here, convergence in measure doesn't care about what the actual values of the function are if they're more than epsilon away from your limit function, right? It just cares that they are more than epsilon away. So the fact that we were able to get the sets on which they differed by more than epsilon small enough, right, and so that they limited to 0, the fact that we're changing the values here and making them larger, it doesn't matter, right? So in fact, we will still get here convergence in measure. Okay. However, we will not have, okay, what we will lose here is going to be convergence in mean. And you can sort of see that, right? We had convergence in mean before, but now, right, this is essentially what I'm going to be looking at, this limit. But now each of these, right, has, when they have base 1/2, they have height 2. So their integrals are 1. When they have base 1/4, their height is 4. So they have integral of 1. So this is actually just each of these limits is just 1. So that converges to 1 and not 0. And so you actually lose the convergence in mean here. Now, another reason for showing you this example, so a couple things we could take away here. We have now seen a couple of examples, and in fact, so the tall spike and now this one, and in fact, the last one, we'll see another one, where we have convergence in measure, but not in mean, okay? That makes me believe that convergence in mean is probably a stronger property than convergence in measure. Again, not a proof, but just sort of an idea that I have. Okay. Again, I sort of feel like these things group together and these things group together. in some certain ways. And finally, I just want to say, right, again, this one fails, convergence in measure. Does that mean it's the weakest one? Well, it means somehow it's relatively weaker than a lot of other things, but it may not be, again, a strict sort of hierarchy of here's the strongest form of convergence and here's the weakest form of convergence. All right. The last example that I want to look at, let me erase first. The last example I want to look at are what we will call the polynomial concentration sequence. So again, you can see what I'm doing here is I'm taking something we've looked at before, x to the n, and I'm just multiplying it by n each time. Okay. So now if I think about what's happening with this sequence of functions, right, before when I looked at, when this was just like x to the n, okay. But now what's happening as well is every time I'm multiplying by n. So I still start, for these, right, I'm still going to start with my n is equal to 1 is going to be the same. But then my n is equal to 2, right, this is going to double, and I'm going to get something like a quadratic. And then that's going to triple, and I'm going to get something like a cubic, and so on, and so on, and so on. All right. So let's see what we can say about these. Now, this sequence will converge pointwise. I'm not going to write a formal proof, but let's think about why. Fix an x value that's less than 1. If x is less than 1, then x to the n is going to go to 0. N is going to go to infinity. This is exponential, right? This is linear. Exponential wins out. So this is going to 0 faster than this is going to infinity. And so for each x value strictly less than 1, we get convergence. Now, when x is equal to 1, this diverges. So I should be careful. We don't get pointwise convergence on the closed interval 0, 1. We get pointwise convergence on the interval closed 0, open 1. But that's enough to say pointwise almost everywhere. The only place it does not converge pointwise is a single point, which has measure 0. All right. What about almost uniform? Well, think back to that sort of n example. Okay, that x to the n example. Similarly here, if I remove an interval around any neighborhood around 1, I can get this to uniform convergence. It's really the same argument, right? So what you do is you show that, okay, here's 1, you remove some interval, say, go to here, right? If you delete all those points, now you're just working on this interval, and you can show that on this interval, your entire sequence will converge to 0, basically however fast this is converging. As soon as you make sure this gets below whatever, epsilon you want, then the whole thing will be below there. So you do get almost uniform convergence because you can always just delete one of these neighborhoods and get uniform convergence on the remainder of the interval. Okay, so you do get almost uniform convergence. Okay. You do not get uniform almost everywhere. Again, very similar to x to the n, right? What happens is you really need to be able to remove a whole interval around 1, not just a single point. So you get that. We get convergence in measure. Okay, so why do we get convergence in measure? Check that off. So for this sequence, to get convergence in measure, okay, sorry, let me get to the right place on my notes here. For the convergence in measure, okay, we just need to look at, I want to look at then the limit as n goes to infinity of the measure of the set of all x such that f sub n of x is greater than epsilon. Well, f sub n of x minus f of x, but the pointwise limit is 0. So really it's just that this is greater than epsilon. Okay. Well, if I do just a little bit of algebra here, okay, This is the same as the set of all x such that I'm just going to mess with this condition for a second. This is the set of all x such that x is greater than epsilon over n to the 1 over n. Okay. And so if I look at the measure of this set, right, I can actually just figure out it's just where x is greater than this. So this is the limit as n goes to infinity, right? This expressed another way is just the set of x values whose lower bound is epsilon over n to the 1 over n. That's the lower bound up to 1. So it's that interval. It's just an interval, so I can just take its length. I guess to be precise, that's a closed. Okay. But I just take its length. Okay. And you can do a little playing around with this this limit here. It turns out that this limit is in fact just 1 minus e to the 0. E to the 0 is 1, so that is 0. Okay. So we actually get that this converges in measure. Now, the reason I like showing you this example is it shows a couple of tricks. One is sometimes you can take these conditions and actually just rewrite them in a form so that they're, if you can solve this for x, essentially, it just becomes an interval condition. So you can easily find the measure of that interval, right? And now this is just some sort of limit problem, right? Like the way you would actually normally solve this sort of thing is to do a log derivative, or sorry, a log limit, right? So you take the log of this and calculate out what this is. Okay. But you get that it's 0 here, and so you get convergence in measure. For convergence in mean, okay, you actually have to do some integration by parts. So if you want to ask about convergence in mean, you need to look at the limit as n goes to infinity of the integral over 0, 1 of n times x to the n d mu. Now, that's Riemann integrable, so you can just do the Riemann integral. This turns out to be, you do integration by parts. Or wait, sorry, no, not integration by, you don't need to do integration by parts, sorry. That's a different example I had in my mind. You can just do this one directly, right? But if you do this directly, you just get that the value is n over 1 plus n over n plus 1, which as n goes to infinity goes to 1, right? And that's not 0. So you fail to get convergence in mean. Okay. So we get sort of, again, we see sort of some splits here. We've got some piecewise, almost uniform. We've got in measure, but not in mean. Okay. So we sort of try to think about what all that means. So what I want to do to finish up this video is I've got the full table of these written out. And let's just talk through some observations. These will be things that will help us next time in thinking about what sort of theorems we might want to try and prove to finish up this section on convergence of sequences of functions. So here's the full table. Okay. Now let's make a couple of observations. Again, the first is, yeah, it does really seem like this uniform almost everywhere convergence is probably the strongest type of convergence. In fact, none of the examples we looked at today have uniform almost everywhere convergence. Okay, so that seems like that must be a pretty strong form of convergence. Okay. Now there are all sorts of observations we can make. Now we could go through these piece by piece, right? And I could say, okay, for example, almost uniform convergence does not imply uniform almost everywhere convergence, right? Example 1 tells me that. So I could create this sort of chart of given these 5 things, which of them could possibly imply the others. Okay. But I can even make more nuanced observations. So, for example, notice that anytime I have a sequence of functions that converges pointwise almost everywhere, it seems like I get convergence almost uniformly, except for this one case. But notice that this one case is the case where I had a domain with infinite measure. In all the cases where I had finite measure, right? If I had a finite measure domain, then it seems like pointwise almost everywhere convergence maybe implies almost uniform. Maybe that's true. Okay. It is true. That's actually exactly what something called Egorov's theorem says. We'll look at that next time. Okay. Seems like anytime I have convergence in mean, I also have convergence in measure, but not the other way around. So maybe convergence in mean implies convergence in measure, but not vice versa. Okay. So again, you start to, I encourage you to take some time to go through what other patterns do you see here, right? That we might want to test out next time, right? It's a really nice way to sort of think through all of these examples. Now, all of these examples are nice examples to just have in your back pocket when you have sort of a hypothesis that you want to test, right? So I wonder if this, when I have a sequence of functions that's converging pointwise almost everywhere, can I say this thing is true? Well, you pull out an example, right, that converges pointwise almost everywhere. And if you really want to test it, maybe you pick out the one that converges pointwise almost everywhere, but not in any other way, right? That'll help you really distill whether, is it really just the pointwise almost everywhereness, or is it something else? Maybe I need pointwise almost everywhere plus, a finite measure space, right? Or maybe I need almost uniform, like maybe I actually need something else, right? So these examples are all helpful in sort of testing things as you move on later in mathematics and want to prove other types of claims. So we'll stop here for this video. In the next video, we want to come back to some of these observations we've made and see if we can formally prove them.